So we are going to go through an example today of a full redox reaction. And we're going to go through the example, which is called, you don't need to know this name, okay? It is called disproportionation. Like I said, you don't need to know it. It's got so many syllables in it. But it is what happens if you have a single species, just one species, that undergoes both oxidation and reduction. So if you look at this reaction here that we're going to be balancing, this is an unbalanced redox reaction. So it includes both the oxidation and the reduction. It's just unbalanced at this point. And remember, this example is in the, it's in the document that I gave you that has like the worksheet questions in it. So you can copy this example down or not as you choose. It is provided to you if you prefer just to listen and watch. Okay, so if it is a balanced redox reaction, there must be a reduction, a half reaction, and an oxidation, half reaction, but we have only one reactant. Yes? So what that means is that some Br2 will undergoes oxidation, and other Br2 molecules undergo reduction. So some of the Br2s are going to be giving electrons to the other Br2s. All right, so when we look at our half reactions, we say half reaction A is going to be Br2 going to HBr. That's going to be a half reaction. And half reaction B is going to be going to HBrO3, okay? And that's going to be our other half reaction. Now, if you had to take a look at these and you had to guess which one is going to be the oxidation and which one is going to be the reduction, so let's call this one half reaction A, and let's call this one half reaction B. Of A and B, who is the oxidation and who is the reduction? Can you tell just from looking at it? Okay, so I've got various answers coming in. Okay, so let's take a look at A. One of the things that I haven't mentioned is that if you just throw hydrogens onto things, that's going to be reduction. If you throw oxygens onto things, throw oxygens onto things, that is oxidation, okay? Oxygens, oxidation. Why is that? Because if you add oxygens, remember oxygen has an oxidation number of -2, and that means that whatever you have attached to it is going to have to be more positive to balance out this negative oxygen. And if the charge is becoming more positive, if the oxidation number is becoming bigger, it has become oxidized. But if you throw hydrogens onto things, that is usually reduction. Why is that? That's because hydrogen, remember, it has an oxidation number of +1. So you have put something on there that's +1. That means that whatever it was before has to become more negative to compensate for that extra positive. And that probably made no sense whatsoever. So if you're like, I don't get that, Ms. Bent, don't worry, it's okay. You can go back to the regular way of just finding the oxidation number and then finding the oxidation number and seeing if it got bigger or smaller. So for both of these, the oxidation number of Br2, what's the oxidation number of Br2? The oxidation number of Br2. Everyone, at least answer it to yourself, even if you don't want to type it in. What is the oxidation number of Br2? Of the Br? Any element on its own, and Br2 is on its own here, right? There's no other element. So if I say not on its own, I don't mean that it's just a Br. It could be Br2. It just means it's not in a compound. We call that its elemental form because it is simply the pure element. Okay, and the oxidation number for any element on its own in its elemental form is 0. Okay. Now, what is the oxidation number for bromine in HBr? What is the oxidation number for bromine in HBr? Well, if we have HBr, you can set up the equation like we've been doing before, or this one's so simple because there's only 2 elements and only 1 of each. You can say if H is +1, which that's its number, then Br must be -1, and most of you are getting that, so that's grand. So Br is -1 here. And then finally, what is the oxidation number for Br in HBrO3? What is the oxidation number of Br in HBrO3? Yes, it is. Okay, so if we were to do the actual calculation on that one, we would have H plus Br plus 3 O's equals, and it's got an overall charge of 0. I'm going to put a 0 with a line through it to distinguish that from that O, which is oxygen. Okay, because that looks like 30, but it's not, it's 3 O's. Hydrogen has a +1 oxidation number that you need to memorize that. Bromide is the one we're looking for, and we have 3 times oxidation number for oxygen is -2, so that gives us that. Then we would have +1 plus bromide -6 equals 0, so that would be bromide. If I take these 2 together, I get -5. -5 equals 0, so bromide is going to have an oxidation number of +5. Okay. So as we go from, let's zoom in here, and I'm actually going to get rid of all of this bit here. Okay. As we go from Br2 to HBr, that half reaction, was that an oxidation or a reduction? is this half reaction here going from Br2, which has an oxidation number of 0, to HBr, where the bromine has an oxidation number of -1. That is a reduction. Yes, it is. That number got reduced. It went from 0 to a smaller number. Okay, and then if we have, oops, there we go. If we are going from Br2, which is 0, to HBrO3, where the Br has a oxidation number of +3, that would be oxidation because the oxidation number got bigger. Okay. So all of that, we didn't really need to do any of that to solve this question, by the way. This was just review because I want to make sure that you guys are good with finding your oxidation numbers, identifying who is the reduction or half reaction and who is the oxidation number half reaction. So I'm actually going to grab this reaction and put it on a different page where I've got lots of space. Okay, so I have Br2 goes to HBr plus HBrO3. And step 1 for solving to balance a redox reaction, what is step 1? What's the first thing we have to do? A step that many people forget. Yes, we have to split it into 2 half reactions. Split into 2 half reactions. So let's do that. We've got half reaction A, and we have half reaction B. So we have Br2 goes to HBr, and then we have Br2 goes to HBrO3. Excellent. So that is step 1, and step 1 is done. What is step 2 in balancing a redox reaction? Yeah, we're going to balance the half reactions. And in order to do that, we're going to balance the major elements, and then we're going to balance O by adding H2O. We're going to balance hydrogen by adding H+, and then we're going to balance the charge by adding electrons. We've done this so many weeks now that I'm hoping that this part here, the balancing of half reactions, is like second nature to you now, or at least it's becoming that way. Okay, so let us balance this, or these rather. So we're going to balance our major atoms. We have Br2, and I've only got one Br on the right-hand side, so we need to put a 2 there. There's no oxygen to worry about, but there are 2 hydrogens on the right-hand side, so we also need to put 2 hydrogens on the left-hand side. In our second reaction, we have Br2 and only one Br over here. So again, we need to have that coefficient of 2 to balance the major atom, the bromine. How many oxygen do we have at this point? How many oxygen do we have? Yes, we have 6. So over on this right-hand side, I add 6 waters. Okay. Now, how many hydrogen ions will I need to add? So how many hydrogen ions, and to which side? How many hydrogen ions, and to which side am I going to add them? Absolutely, yeah. Yeah, because we have 12 here, and over here we have 2, then we need to add 2 hydrogens over here. Get rid of that because it just makes it messy. Bye. And get rid of this. And then finally, we need to balance our charges. Oh, I didn't do that on my top one. Oopsie. So for balancing charge on the top, I've got 2 electrons on the right because this one's pretty easy. I've got a 0 charge over here, and over here I have 2 positive. So I need to add 2 negative to make it neutral. And that means that in my second half reaction, if I have electrons on the left-hand side over here, my electrons in the other one should be on the right-hand side. If I have both electrons on the left-hand side, and like let's say I had some electrons over here, that would mean that I have done something wrong. There's no way I can have 2 reduction half reactions or 2 oxidation half reactions. Okay, so the electrons are going to have to be over here. And in fact, that is correct because I've got 2 H plus, so there's going to be 2 electrons there. And oh, hey, what is step number 3 for balancing full reactions? Step number 3. Yeah, we need to balance the electrons. Make sure the electrons going in equal the electrons out. Okay, or you're finding the LCM. And in this case, oh, look, I have 2 and I have 2. Ha, 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 super easy. Excellent. What do I do in step 4? I'm going to add it up and cancel. Yes, add up and cancel. So I'm going to put them back together. So we're going to take our 2 half reactions and we are going to add them back together. Oh, that looks like a really weird plus sign. Don't like it. There we go, that's better. So our 2 electrons over here will cancel with 2 electrons over here. Our hydrogen over here will cancel with our 2 hydrogen over here. And then finally, we need to add things up. One thing that I've noticed sometimes people like to do is they want to cancel this bromine on the top with this bromine on the bottom. Can we do that? Can we cancel those 2 bromines? No, because they are both on the same side. So instead of canceling them, we're going to actually end up with 2 Br2 here because we have 1 up here and we have 1 here, and that gives us the 2 there. Okay. And in addition to the Br2 on the left-hand side, we have, oopsie, we have 6 water. Okay, that comes down. And over on the right-hand side, we have 2 HBr plus 2 HBrO3. Okay, so if you have only 1 reactant, that just means it will be the reactant for both half reactions. Okay, don't panic. It will be the reactant for both half reactions. Okay. All righty. Last example we're going to do today. There it is. No, that one. There we go. No, that one. Yes. Disproportionation. There we go. Now, you might have something where instead of just having 1 reactant, and you're like, what do I do with that? You might have more than, you might have lots of products over here. You could say, okay, well, it's pretty obvious that when I'm splitting up my half reactions, my manganese is going to turn into the permanganate ion. But what's going to happen with my iron? What are the products of that half reaction going to be? Well, there won't be one product, there will simply be two products. Okay, so this half reaction has, the top half reaction has one product, and the bottom half reaction has two products. And other than that, it's just identical to every other example we've done. So step one, we're going to split into two half reactions. So we will have our Mn3 plus going to MnO4 minus. Okay. We will have our second half reaction, FeSO4 goes to, and now we say, okay, I've got Fe's in my reactants, I've got S's in my reactants, so I will be making the Fe's over here, and I will be making the S's will show up in the SO2. So that's the only thing that's different. And now we're just going to balance the half reactions. And that's the major OH says charge. Okay, so our major atoms in reaction number one, manganese is just one on each side. In our second reaction, iron is just one on each side, and sulfur is just one on each side. So we don't have to do anything for the major atoms. Oops. Oops, making a mess. There we go. Okay. Now we have to balance oxygen. So actually, maybe let's just do the top one on its own first. So we have 4 oxygen on the right-hand side. So we're going to have 4 H2Os over here. That gives us 8 hydrogens on the left-hand side. So we need to have 8 hydrogens on the right-hand side. Our total charge on the left is 3 positive. Our total charge on the right, I have -1 and +8. -1 and +8 is +7. Yes. So I need to add electrons to the side that has too much positive charge, so that's over here. And I'm trying to get it down to a 3+ charge, so I need to add 4 electrons. Balancing our second one, pardon me, we have 4 oxygen on the left, 2 oxygen on the right, so we need to have 2 water. Balancing hydrogens, we have 4 hydrogens here, so we need to have 4 hydrogens here. And that means we also need to have 4 electrons on this side because the charge over on the right was 0 and the charge over on the left was 4+, so we need those 4 electrons to balance that out and give us 0. Oh, look, my electrons in equal my electrons out. I'm feeling like this is way too easy, but that's okay. You'll have different examples where the electrons in will not equal the electrons out. Did I do something wrong? Is it possible? I don't know. Okay, well, that's all right. Those will cancel out, and then we have Mn. We'll just add them back up. Mn3 plus 4 H2O plus FeSO4 plus 4H plus goes to MnO4 minus plus 8H plus Fe plus SO2 plus 2H2O. Now I could have done my canceling earlier. Maybe I should have, but I didn't. At this point, I will do my canceling. So from the left-hand side, we have 4 water here, and we have 2 water here. So we're going to cancel out 2 of the waters. It's going to leave us with 2 waters there. We have 4 hydrogen here and 8 hydrogen on the products. And so we're going to cancel out 4 of the hydrogen. That'll leave us with 4 hydrogen there. I'm just going to rewrite this because I want to make it, I'm just going to rewrite it. There we go. Mn3 plus 2 H2O FeSO4 goes to MnO4 minus plus A4 H plus Fe plus SO2. Okay. I'm just going to make it small momentarily so we can go back to the question and say, have we fully answered that question? Have we answered the question that is asked to us? No, we have not. Excuse me, sorry. We have not, because we are asked to do it in basic solution. What do we have to add to make it basic? OH. How many? 4. To which side? Well, we have to route it to the right, but we also have to add it to the left. It has to be to both sides. Otherwise, it's like if I had a set of scales and it was balanced and all of a sudden I add 4 hydroxide to the right-hand side, it's going to be unbalanced now. Okay, so we have 4 hydroxide here. Post-nasal drip, not COVID. Where'd we go? Mn3 plus 2H2O plus 4OH minus, make that a bit bigger, plus FeSO4 goes to MnO4 minus, plus these 2 guys get together and they make, what do they make? Water. So we have 4 waters, and then we have our Fe and our SO2. Are we done? We are almost done. We're missing just one little wee tiny itty bitty thing. Yeah, we got to cancel out anything that needs to be canceled. So there's 2 waters over here, and that'll cancel 2 of those waters. And now we are done. Have we forgotten anything else? What should you do at this point when you're like, yeah, I'm done? You should check. Okay, check and make sure everything works out. Start by checking the charge. If the charge doesn't work, then you're pretty much screwed and you got to go back and like look at things, right? Over here we have 3 positive and 4 negative. So 3 positive and 4 negative gives us a -1 charge on the left. On the right, oh look, we have a -1 charge. Yay! So it's looking good. Let's go and check our major atoms. We have 1 manganese, 1 manganese. We have 1 iron, 1 iron. 1 sulfur, 1 sulfur. And let's check oxygens. 4 oxygens on there, and another 4 oxygens gives me 8 oxygens on the left. On the right, we have 4 oxygens and 2 oxygens and another 2. So 4 and 2 and 2 is again 8 oxygens. Yay! You would not normally write this down. You just kind of do it in your head, of course. And then finally, hydrogens. 4 hydrogens here. 2 times 2 is 4 hydrogens there. Yes, we're good to go. Okay, so this week we have a quiz. Okay. Let's see, we want to go here. So this week, the homework, number 1, is the quiz on half reactions and oxidation numbers. So I don't want to give you too much in addition to that. So I will say from 11 through 13 and 17 through 19.